So yeah, thank you for this opportunity. I'm very happy to be here. My name is Farhan. I'm a PhD candidate at New Mexico State University, working with Joe Burchett and some other folks. I will present some work on the impact of cosmic web structures on galaxy quenching across cosmic time, and this is close to being submitted, so fingers crossed. Okay, so as we all know, the cosmic web is composed of filaments, nodes, sheets, and voids. In this talk, I'll be focusing on the filaments and the nodes of the cosmic web. And we know that these large structures connect galaxies to the intergalactic universe. However, the nature of this connection is still being debated. And so we want to understand how large-scale structures affect galaxy formation, which is something that happens on much smaller scales, right? In particular, we investigate the impact of cosmic web on quenching of star formation in galaxies, the cessation of star formation, as functions of galaxy mass and redshift. Okay, so to address our research problem, we look at the illustrious TNG cosmological magnetohydrodynamical simulations, which I think you're all at least a little bit familiar with. We used a high-resolution version of the TNG 100, which has about 110 megaparsecs per side. And shown here are visualizations to show you what the simulations look like, now that you don't know what they look like. TNG 100 redshift 0, and this is rendered using our visualization and analysis software that our group developed. It's called CosmoViz, and you can check it out for yourself and play around with it if you'd like. CosmoViz allows us to look at the simulations through many different viewpoints, and I'm presenting 4 of them here. So we're looking at the gas that is color-coded by gas temperature, gas density, pressure, and entropy, and some of the small bright yellow dots are the star particles in these simulations. So I'll be using CosmoViz. I'll be referring to visualizations of CosmoViz throughout this talk, just as visual aids. I hope that's all right. So for this work, we're using a sample that has all galaxies with stellar mass of at least 10 to the 8 solar masses at all snapshots. Okay, so we reconstruct the cosmic web with disperse, and I won't go much into what it is because I think we've all heard a bunch about disperse so far, but as you know, it uses the topology of space to reconstruct cosmic web structures. So we input some galaxy positions. This gives you a density field, and this eventually generates a catalog of critical points, including nodes and filaments. So disperse operates on the concept of persistence, which is a measure of how robust your identified structures are to shot noise in the input data. And so based on previous work with TNG, we choose a persistence of 3 sigma, because any less than that, and you probably pick up some spurious features, and any more than that, you might miss some of the fainter structures. It's kind of a middle ground. Okay. So now for like a qualitative look at how the cosmic web and galaxy star formation evolves from high to low redshift. So this is a 2D projection, and the galaxies are the dots in the background, color-coded by specific star formation rate, and the filaments are the black curves, and those magenta stars are the nodes. As you can see, with time, the number and clustering of structures increases significantly, but the star formation also evolves. I don't know how clear it is to you guys, but galaxies get less star forming in general. And also you see these redder dots, right? These very quiescent, effectively quenched galaxies that appear at low redshift. And qualitatively, you can see that they appear near these, dense filamentary connections. So anyway, this is just a visual look. Or a qualitative look. Let's quantify this more. And to do this, we measure 2 different distances of a galaxy relative to the cosmic web. One of them is d node. That's the distance of a galaxy to the nearest node, which would presumably correspond to a cluster or a group, but as we heard earlier today, there are caveats to that. And the other is dfil. This is the transverse distance of a galaxy to the nearest identified filament spine. So we measure star formation properties relative to these distances. And so let's start with the results now. Starting with star formation as a function with respect to nodes. And shown here below is a visualization of how a node environment looks like, what a node environment looks like in gas temperature. So these plots above are the median specific star formation rates in different bins of distance to the nearest node and in different redshifts, right? Each of the colored data points correspond to a redshift, going from redshift 0 all the way to redshift 4. The plot on your left, that's for lower masses, with stellar mass 10 to the 8 to 10 to the 9. Plot in the middle is for moderate masses, 10 to the 9 to 10 to the 10 in stellar mass. Okay, so we see some interesting features here, starting with at low masses, galaxies are quenched close to nodes within 1 megaparsec node. At low redshift, these galaxies are quenched as indicated by these upper limits. Even for moderate mass galaxies, there's an order of magnitude drop in star formation from high D node to low D node. But look at those higher redshifts, right? The magenta line and above, you see a flat line indicating no relationship between specific star formation rate and D node at higher redshift. And this is where these color contour plots on the bottom right come in. So that basically these show these relationships at each of the redshifts from redshift 1 to redshift 3. And the way to look at it is at what point does this contour flatten out, right? Just to show you that, okay, this happens at some point between redshift 1 and redshift 2, where the dependence of star formation on D node disappears. And it happens above redshift 1. And for higher mass galaxies with stellar masses above 10 to the 10, we again see no dependence of star formation on D node above redshift 1. At lower redshift, though, we see something interesting, right? There's this upturn in star formation at very low node-centric distances, the lowest D node bin, which is interesting. And as we've already heard, we actually expect, for various reasons, for there to be a continued decline in star formation close to nodes. So this is an interesting feature, and as you can see, it kind of persists up to like close to redshift 1.
You kind of trace this upturn all the way to redshift 3.
Yeah, you can, but I can only confidently say that this happens at redshift 0. Yeah, but anyway, so there are these interesting correlations we can see. So we want to break this down further and look at central galaxies versus satellite galaxies, right? And so these plots are those same star formation D node plots, but for central galaxies and for lower masses. As you can see, only perhaps at redshift 0 is there an effect of D node on the star formation of low mass centrals. There's really hardly any effect on low mass centrals. But looking at satellites, this is a significant effect, right? Close to nodes, low mass satellites are completely quenched, and there's at least an order of magnitude drop from high D node to low D node at low redshift. So that decline of star formation close to nodes at low redshift is driven by satellites more than centrals. For higher mass galaxies, so these are the panels on the right, you see this upturn, and for both centrals and satellites, right? For centrals, you see that upturn at redshift like 0.5 and redshift 1. There's upturn at low D node. And for satellite galaxies, there's significant uncertainties, of course, but there's still that upturn signature of at redshift 0. So both satellites and centrals drive this. But once again, this big point remains, right? That there's no dependence of star formation on D node at high redshift, above redshift 1 or so, for either centrals or satellites. Okay, now we look at star formation with respect to filaments. And so for this analysis, we exclude all galaxies within 1 megaparsec of a node. This effectively means that we're tracing more intermediate density environments compared to the more denser environments near nodes. And here's a visual again from CosmoViz of such a filamentary environment in gas temperature. So looking at the filament-centric relationship for the highest mass galaxy range, we see that there's only a moderate decline, a small decline, right? Not as intense as before, a small decline at low, with proximity to filaments at just the lowest redshifts. Let's see what happens for lower masses, and you see that for low mass and high mass bin, there's that gradual decline with proximity to filaments. Nothing exceptional, but just a little bit at low redshift. And then once again at high redshift, flatlined, right? There's no relationship between star formation and distance to the nearest filament. And we break this down too into centrals and satellites. And for centrals, I'm showing all the panels here because they essentially show the same thing for all mass ranges. Hardly any effect on low mass centrals of low mass centrals close to filaments in their star formation for any mass or any redshift. Low mass satellites, the only effect we really see is at lower redshift and same thing for high mass satellites. You see an effect for at lower redshift, they're quenched near filaments. But once again, this holds true, right? There's no dependence of star formation at higher redshift for either centrals or satellites relative to filaments. Okay, so since we know that the gas supply or the star formation of galaxies proceeds from the available gas supply, we also looked at the gas fraction, which is just the mass of gas that's bound to a galaxy divided by gas plus stellar mass. And we plot these median gas fractions in the same bins of D node as before, in the same three mass ranges as before, but now we're only showing it for 4 different redshifts, 0, 1, 2, and 4. So what we notice is that for lower and moderate mass galaxies, there's a rapid drop of gas fraction as you get close to nodes, and this could at low redshift, and this could possibly explain why there's rapid quenching of star formation close to nodes at these redshifts with these masses. At high masses, you see a huge dramatic upturn of gas fraction close to nodes, which could potentially explain why there's an upturn in star formation close to nodes. Except note how the rise, this upturn in gas fraction is a lot more dramatic than the upturn in star formation. And we broke this down too into centrals and satellites, starting with the lower mass centrals. And as we saw with the star formation case, low mass centrals seem to be hardly affected by proximity to nodes, hardly affected in their gas fraction, that is. Low mass satellites significantly affected. At low redshift, you see the low mass satellites, are devoid of gas, so they don't have gas as they get closer to nodes, which is why they stop forming stars. That's the connection there. And looking at higher mass centrals and higher mass satellites, we once again see this curious upturn of gas fraction close to nodes, both for centrals and for satellites at lower redshifts, which again could explain why there's an upturn in star formation at those locations. And finally, just to round up this exercise, we also look at how gas fraction is affected by distance to filaments, and as you can see, there's just like a gentle drop in gas fraction at low redshift as you get closer to filaments. And this is nothing fancy, it's just a small drop, and this could explain why there's correspondingly a small drop in star formation close to filaments. Okay, so why does this happen, right? So I want to discuss a little bit of the physical mechanisms that can manifest these trends that we find. So there's something different happening at low redshift than at high redshift, it seems like. Low redshift meaning less than redshift 1. At these redshifts, it seems like low mass satellites are the ones that are suffering the effect of quenching due to cosmic web, and this is because they don't have enough gas. So something's removing the gas from these galaxies, and so there's a bunch of physical processes that could be at play here, including ram pressure stripping or tidal stripping in dense environments, or outflows from star formation, which could remove gas on very short timescales. And then there's starvation effects, which prevent the accretion of gas onto the ISM, and this happens on longer timescales. And these could all collectively lead to gas being depleted and quenching in these galaxies. For high mass galaxies, we saw something different, right? Star formation is enhanced in high density environments, and this could be due to rejuvenation effects, whereby a lot of gas is funneled into these galaxies, which causes temporary bursts of star formation, or this could just be a numerical effect caused by the simulation and the physical modeling in the simulation, and not something that is based in reality. At high redshift, above redshift 1, things change, and it is plausible that cosmic web structures at these redshifts can actually allow more gas accretion and actually raise star formation in galaxies. And this argument has to do more with how, for example, cold streams can penetrate the halos of more massive, or penetrate the halos of galaxies at high redshift much more efficiently than they can at low redshift. In any case, our results suggest a cosmic phase change in the environment quenching, in the cosmic web environment quenching connection past the cosmic noon of star formation. Okay, and so we're following this up on multiple fronts. And so one of the projects we're working on right now is to understand this better is really just studying gas conditions, understanding how the gaseous conditions as imprinted in the temperature, entropy, and so on, how that could influence quenching in these galaxies. And I'm referring to gas conditions in the filaments and nodes, not just a CGM of galaxies. And here are just some examples of visualizations again from CosmoViz. You can see a visual analysis reveals some interesting pattern signatures. For example, there's volume filling ubiquitous warm hot gas in filaments, but then when you look at entropy, there are these distinct shells of high entropy, more orange stuff at the shells that encases lower entropy gas near the centers. And these shells are presumably the locations of accretion shock, or signatures of accretion shock heating. And so one of the things we're investigating is how that could influence quenching in galaxies that are near them. So we're following this up with particle data analysis as well. And finally, we will be reconstructing the cosmic web with our own cosmic web reconstruction tool developed by collaborator Oscar Elek at UC Santa Cruz. And this tool is called, this software is called the Monte Carlo Fizer machine, MCPM. And I wish I had time to go into what it does, but I don't. So please do take a look at these papers. But essentially, it mimics the feeding habits of this organism called the slime mold, and it's actually reproduced the cosmic web pretty well in simulations and observations. So we'll be using that to compare our cosmic web reconstruction, the cosmic web reconstruction from disperse, and see how that varies. And finally, here's just, Oscar could not be here, but so on his behalf, here's just an advertisement of this cool new project that's on GitHub. And so basically, this is a interactive visualization software called Polyphi, which uses the MCPM algorithm, and you can play around with it yourself. But we're looking for collaborators, either to contribute to the code or to use the reconstructions from MCPM. So anyway, this is a summary of my talk. I'll just say that there seems to be, we've uncovered some results which suggest that between redshift 1 and between higher redshift and below redshift 1, there seems to be a change in how galaxies, the star formation of galaxies depends on the cosmic web. We're not exactly sure how this happens, but it's what we find. And I'll end by saying that our results yield important predictions to be tested with current and future observational data from DESI, SDSS, Roman, and so on. And I'll take questions.
Thanks very much, Farhan. We have lots of questions.
Hey, thank you very much for the presentation. That was nice. When you look at the redshift dependence of the effect of the cosmic web, there is a confounding factor, which is if you look at a 10 to the 10 galaxy nowadays, and at redshift 4, you're either looking at a not very rare object compared to a very rare object.
Yeah.
Which means that essentially how it scales compared to the cosmic web is completely different.
Right.
So maybe one thing you could try is to, have you look at like dividing that, for example, by the nonlinear mass, which somehow like rescales everything into what you would expect to be either rare or not rare. Because that may show that this redshift dependence is just the fact that you're looking at either very rare object or not rare objects. Okay.
Yeah, no, we have not done that analysis, but thank you for pointing that out. Yeah, I mean, I do know that, you know, a halo, a same mass halo at redshift 0 is not the same as the same mass halo at redshift 3, right? Same goes for filaments, right? Filaments at redshift 0 are not the same as filaments at redshift 3. We just do a geometric analysis. We don't do any specific analysis of those things, yeah.
Hi, great talk. I'm looking forward to the MCPM comparison with disperse. But my question was, I'm a naive observer. I have no idea how Illustris works. So maybe you could shed some light on what exactly it's doing for star formation. Like, what is the prescription underlying there? And well, I would imagine that it should be part of the documentation that how it's related to the gas density, is it not?
Yeah, you're talking about TNG, the
Yeah.
TNG model?
Yes, the model that you used.
Yeah. Yeah, I mean, yeah, so, you know, TNG is known to do a pretty good job at reproducing a lot of observations, stellar mass function, and so on. And yeah, and so, you know, there's two kinds of feedback. There's stellar feedback, you know, stellar winds, supernova, that kind of stuff that acts on lower mass galaxies, and that can sort of regulate star formation. Those galaxies in higher masses, you have black hole feedback, and black hole feedback can be, you know, more explosive, or it can be more kind of, you know, steady, depending on like where it is in that AGN feedback cycle. I do know, and so, you know, there's like the physical things that are happening are actually included in the model. The physical things we know of, they are included in the model. However, TNG does have one problem with its star formation statistics, which is that it seems to quench galaxies too quickly, right? Like there's not a good match between Green Valley galaxies. Like it doesn't produce enough Green Valley galaxies, and this could be because it just, you know, the black hole feedback is so intense that blows away a lot of gas, and it just quenches galaxies way quicker than what is real. So.
Beautiful talk. You said, well, you said that the next step is going to be comparing with the MCPM. But did you at least qualitatively compare with the previous study by Martisi et al. That looked at the Hessian classification?
Yeah. No, I did. Martisi, like 2019 or 2020, yeah. I think. Yeah, that was a great paper. Yeah, I think we found, so, you know, the stuff where it's, you know, quenching is increasing with proximity to cosmic web. I think our results are comparable to theirs. I don't think they uncovered this signature though, this upturn of star formation at very high density environments. Maybe someone can correct me if they're more familiar, but as far as I recall, that was not the case. And I don't know if they found a strong signal or strong lack of this signal of cosmic web dependence at high redshift, which we found not to be a signal. So, yeah.
I have a very naive short question. How was the entropy defined in these plots? So how is it computed?
Compute the what? Sorry?
Entropy.
Oh, yeah. Yeah. So entropy. This is one of the. This is in the particle data in the TNG simulations, right? And essentially, you know, you assume. Someone can tell me what that the symbol means, but there's a gamma, there's an adiabatic factor, but basically you use the pressure entropy relationship, and and that's it. Yeah, and you know, you have gas pressure that you compute for each gas cell, and you apply that to entropy. Yeah.
I'm very surprised to hear your result, which is exactly the same as mine. So I'm going to talk about it a little later. But what is special about the epoch is equal 1?
That's a great question. That's something I've been thinking about for months. Well, I mean, so I think one of the previous talks, I think Rico's talk, showed that Maddow-Dickinson plot, the cosmic star formation history. And redshift 1 is really the point where, you know, maybe redshift 1.5 is where that peak, the cosmic noon of star formation is like, you know, you're no longer at that peak. And so at that point onwards to the present day, star formation activity just keeps decreasing. And I also think below redshift 1, there's a lot smaller contribution to the UV background from AGN, as far as I understand. That's like I can't think of anything that's special in terms of the cosmic web that's at that redshift. When? That's roughly when shell crossing. Oh, okay. Okay. At redshift 1? Around that 1. Huh, okay. Interesting. Yeah, one, yeah, like.
Hey, really cool how you pulled all of the elements apart. I look forward to looking at that again with more time. So I'd like to know a bit more about the time evolution of your dispersed networks.
Yeah.
You showed a video at the beginning there where it was jumping around a bit, became more complex as time moved on. Yeah. I don't know if this is intuitively, I think I would feel it's the other way around. And earlier today in Hannah's plots, we saw how behaved it looked. So how can you comment on that? Let's put it that way.
Comment
on this, yeah, because all of your defills depend on what you did here, right?
Yeah.
So is this how we imagine the filament network to evolve?
Yeah, that's a great point, and I think you and my advisor would have a lot to talk about that. Yeah, but yeah, I don't like. I agree. Yeah, there's some jumping around, and
just this thing like goes fly, and it won't move.
right.
Yeah.
Yeah. No, I agree. There's some jumping around the filaments. Like filaments shouldn't just spontaneously appear and disappear within 10 million years or whatever, 100 million years or whatever, right?
Actually, maybe that might be a good test to see if you only look for the really big persistent ones, if your results hold.
Okay.
I don't want to suggest to do it before you submit, but no, yeah.
Totally.
Well, in 2009, just when we finished Disperse, we wrote a paper computing a Lyapunov exponent related to the positions of filaments. And the position of filaments themselves are stochastic variables. I mean, they have a positive. But if you impose a tighter persistence level, they won't move. So it's your choice which induce these fluctuations.
Okay.
I mean, it's just if you think. Don't think of disperse as tracing filaments. Disperse is finding ridges, and you can have small ridges in a lake or whatever. And if you impose a low level of persistence, it will pick it up. That's your choice.
Right.
I had a question. You look at the gas density. Have you considered looking at the gas density which triggers your subgrid physics star formation? So putting some threshold on, because in that case you should recover at the macroscopic level what you input at the cell level. The only parameter which is extracted from the simulation, I guess, is the freefall time. But the threshold for star formation is directly encoded by you or by the person who ran the simulation. Right. So it would be interesting to redo these plots with the threshold of star formation as given by the simulation.
Absolutely, yeah. So just a correction, this isn't density, it's just gas fraction, just content, right? Amount of gas relative to the total baryons. And so, yeah, we haven't done any cuts of, like, for example, gas temperature or gas density thresholds. I think that's a very interesting, that's partially why we're looking at particle data right now, to actually do that computation and all these elements, yeah.
Have one last question. I think you were the first over there.
Thank you. Great talk. I'm wondering whether the uptime feature is dependent on the virial mass of halos at nodes.
Yeah. That's a great question. One of the co-authors, Joe Premack, he's had that same comment earlier. I think there's some work that shows how at least in some simulations, cosmic web dependence of galaxies could actually just be due to halo accretion, right? Halo mass accretion. And so it's a question of, like, is this specific to the baryonic physics involved in galaxy formation, or does this all just really kind of follow from dark matter halo accretion?
Right. Let's thank Farhan again.